Okay.
Serge Cantat from the University of Rennes, who needs no title.
Thank you. So I want to describe the dynamics of automorphisms of complex projective surfaces. So that's what I want to do. But first I want to explain what an automorphism is, and also what a projective variety is. So automorphisms okay, so you take X, say a smooth complex projective variety. So this means that X is contained in some projective space over the complex numbers. It's defined by a set of polynomial equations which are homogeneous, and polynomial equations in the homogeneous coordinates in Pn. And as a complex variety, it's a smooth complex variety. Okay, and then the group of automorphisms of X. So you have two viewpoints. It's just, so let's say it's a group of automorphisms. That's what I mean by out of X. So, and an automorphism is, so you have two viewpoints. The first viewpoint is that it's a regular transformation from X to X, which is invertible, and the inverse is a regular transformation from X to X in the sense of algebraic geometry, or also it's a holomorphic diffeomorphism of X. Okay, it's the same. Okay, so I want to describe a few properties of this group. So this group is a topological group. So it's a topological group. The topology is a topology of uniform convergence for maps from X to X. But with this topology, it's a complex Lie group. Okay, so more precisely, this one, yeah. More precisely, you can look at the connected component of the identity. So you have a topological group. So you can split the group into connected components, and you can look at the connected component which contains the identity. So it's a normal subgroup in this group. And this group is a connected finite dimensional Lie group, complex Lie group. The Lie algebra is the algebra of holomorphic vector fields on X. But the interesting point for us is that the number of connected components may be infinite. So you can look at the discrete part of this group. The discrete part is just the quotient here. And it may happen that this group is infinite. So I will describe examples. If you take the example of varieties of dimension 1, so compact Riemann surfaces, algebraic curves, then if the genus is 0, the curve is just the Riemann sphere or the complex projective line, and the group of automorphisms is just a group of Möbius transformations. It's PGL2 of C. Okay. So it's a connected Lie group. If you take an elliptic curve, genus 1, then you have the group of translation that's connected, and then you have a finite group for the discrete part. So typically you get the transformation z goes to minus z on the elliptic curve. And then if the genus is 2 or more, then this group is always finite. Okay, so your group of automorphism is finite. So the number is bounded by 42 times the absolute value of the Euler characteristic of the curve. But in higher dimensions, it may happen that this group is infinite. And this is precisely in this case that we will see an interesting dynamical behavior. And I want to describe the dynamics that we can get. Okay, so first I want to give examples. So examples in dimension 2. Okay, so the first example is on tori. So you start with an elliptic curve, C mod lambda. So lambda is the lattice. And now you consider the abelian variety, so the torus E times E. So it's a two-dimensional complex torus. And it's a quotient of C2 by the lattice, which is just lambda times lambda. Okay. So the group of linear transformation with integer coefficients. So this group acts linearly on C2, and it preserves the lattice lambda times lambda. Okay. For all lattices. So this group acts on A. And this gives an embedding of GL to Z into the discrete part of the automorphism group of A. So inside the automorphism group of A, you have the group A. So A is a torus, so it's a group with the law is the addition on the torus. So A acts on itself but by translation, and this is contained in the connected component of the identity. But this part embeds in the group of automorphisms of A and also in the discrete part. Okay. So let me describe the dynamics of one of the elements of this group. So you take the matrix 2, 1, 1, 1. Okay, so that's an element in GL to Z. So the trace is equal to 3, and the determinant is equal to 1. So you can compute the eigenvalues. So eigenvalues are, so the matrix is conjugate to lambda 0, 0, 1 over lambda, where lambda is 3 plus square root of 5 divided by 2. Okay, so it's bigger than 1. Okay, so now the dynamics is the following. So first the dynamics on C2, so on the universal cover. So you have C2. So you have two eigenvalues, one which is bigger than 1 and another one which is smaller than 1. So you have two eigenlines. So that the eigenline for the eigenvalue lambda, and here for the eigenvalue 1 over lambda. Okay, so the dynamics on this line is just a dilatation, so it's an expansion here, and here it's a contraction. And you have two, and now you can project this picture in the torus. So you take the quotient by the lattice. So I'll draw a real picture. So here is the torus. And the projection of this line, so here is the projection of the origin. And the projection of this line is a curve in the torus, but this curve is dense in the torus. Okay. So this curve corresponds to the unstable manifold of this fixed point here. And the one which is a projection of the eigenline with respect to the eigenvalue 1 over lambda, so here, so the projection of this line is a curve which is dense in the torus, and it's the stable manifold of this fixed point. Okay. So it's even better here because you have the set of lines which are parallel to this eigenline form a foliation of the torus by lines. So it's a holomorphic foliation of the torus. And the leaves of these foliations are the unstable manifolds of the transformation induced by the matrix 2, 1, 1, 1. Okay. If you take a point, so x, y in C2, and such that M of xy is in the lattice for some integer m, okay, then the orbit of this point is periodic on the torus. Okay, so if you, let's say, if you tensorize the lattice by Q and take the projection, take the set of rational points on the torus, rational meaning that some multiple is in the lattice, then you get exactly the set of periodic points of the transformations. Okay, so periodic points are dense. All of them are saddle periodic points. And the stable and unstable manifold of these periodic points are leaves of two holomorphic foliations. Okay, so that's easy to describe. But it's a good example to keep in mind. Okay, the second example is the following. So you take P1 times P1 times P1. So it's a three-dimensional manifold. And inside this, you take a surface X. And you suppose that the degree, so you have three projections, so you have 3 degrees. So of degree 2, 2, 2. So this means that, so if I fix coordinates here, x, y, z, so in the affine part, let's say c times c times c with coordinates x, y, z, x is just the set of zeros of a polynomial equation where p has degree equal to 2 with respect to the variable x and also the variable y and also with respect to the variable z. Okay. So geometrically this means that the surface x is in P1 times P1 times P1, and if you project the surface, let's say you forget the z coordinate and you project to the xy plane, then you get a 2-to-1 cover. Okay, and the same is true if you project it on the xz plane or yz plane. Okay, so you get 3 2-to-1 covers. Okay, so I suppose that this surface is of degree 2, 2, 2. And I assume also that x is smooth. So then you have 3 involutions on the surface. So if I take a point x, y, z on the surface, so a point here, I can take the transformation of this point by the involution which correspond to this 2-to-1 cover. Okay, so this means that you fix x and y, then you look at the equation with respect to the z variable. It has degree 2. You already has one solution, then you take the second root of this polynomial equation. Okay, so you get a second point, x1 z prime on x. So it's just involution which permutes the 2 points in the fiber. So above the ramification locus of the projection, of course, you get a curve of fixed point for this involution. So let me denote this involution by sigma index z. So I described a first involution, but you have three involutions, one for the projection on the xy plane, and one for the projection which forgets the y variable, and the third one which forgets the x variable. Okay, and the statement is that when, so here you can choose p generically among the set of polynomial p in x, y, z with degree 2 with respect to each coordinate. So you choose p generically, then the automorphism group is, so for a generic choice of the equation, the automorphism group is generated by these three involutions. And in fact, there are no non-trivial relations between these involutions. So it's z mod 2, product z mod 2, product z mod 2. So it's a free product. Okay. So this group is infinite. It contains a finite index subgroup, which is a free group with two generators. So where is the... Okay, so that's the second example. Let me say two things regarding the geometry of X. So X, you can prove that X is simply connected. And you can also show that there exists, so on X, there exists a holomorphic 2 form. So omega, locally it's like, you can write omega as phi of xy dx dy, where x and y are local coordinates on X, which does not vanish. Okay.
This x and y has nothing to do with the xy.
Yes, that's why I insisted. So x and y are local coordinates on X. Okay, not the global coordinates here, x and y. Okay, so to prove the first one way to prove it, so if you project X, let's say on the Y line, okay, so then you get a fibration, X fibers. So if you take a point here, the fiber here is a curve. In fact, you can prove that it is, for a generic choice of the point here, it's a smooth genus 1 curve. But there are singular curves. Okay? In this fibration, some of the curves are singular. So you can compute the fundamental group. What happens basically is that you can show that the fundamental group comes from the fundamental group of the fiber, but at the same time, all generators become trivial when you move to the singular fiber. Okay. So that gives a proof of the first one, or that's one way to prove it. The second way, the form is easy to define in local coordinates here. So omega locally is dx. So now I use these coordinates, dx, dy, divided by partial derivative of p with respect to z. And you can prove that this local formula, which is valid where partial derivative of p is not 0, in fact defines a global holomorphic 1 form which does not vanish. So this, if you know a little bit of the classification of complex surfaces, this means that X is a K3 surface. So it's a surface which is not biholomorphic to a torus, or not birationally equivalent to a torus. Now let me give another example. So you start with, so this one is due to Jérémy Blanc. So you start with a cubic curve. So So a smooth cubic curve in P2. And then you choose a point Q on the cubic. So first, what I want to do, I want to define an involution which depends on Q and C, an involution of the plane. It will be a birational transformation of the plane. So I will define an element of the group of birational transformation of P2, which will be an involution of fixing the curve C pointwise. So how does it work? So you take a point M in the plane, and I want to define the image of the point M. So I draw the line between M and Q. Okay, so this line intersects the cubic curve in 3 points because C is a cubic. One of the points is Q, and there are 2 remaining points, say A and B. But now if you have a line, so the line is a P1, if you have a line and you have 2 marked points on the line, there is a unique involution which fixes a unique involution of the line which fixes A and B. If A is 0 and B is infinity, this is just Z goes to minus Z. Okay. So eta Q of M is the image of M by the unique involution of the line QM, which fixes the pair of points A, B. Okay? So this defines an involution of the plane. So it's birational. So what are the problems? For instance, if you take a line which is tangent to the cubic, then I don't have a pair of points on the line. So I cannot define this involution like that. So in fact, here I have an indeterminacy point. So there are 4 indeterminacy points coming from the 4 tangent to the cubic going through the point Q. And also there is a problem with the point Q itself. Okay, so in fact, there are 5 indeterminacy points. The second property is that if I take a generic point on the cubic, then by construction, the involution fixes this point. Okay, so this transformation is an involution which fixes C pointwise. Okay. So now I can blow up the indeterminacy points of the transformation eta. Okay, so here I have the plane, and so there are 5 indeterminacy points on the cubic, and I blow up these points. So I have a new surface with 5 exceptional divisors. So these curves are just the blow up of the 5 points. Okay. And it turns out that on this surface, eta is now a regular automorphism. So here I have transformation eta, and here I have the lift of eta. And this one is, so you can prove that this one is a regular automorphism of this surface. Okay? It is just an involution. Okay? So from the dynamical point of view, it's boring. But you can, instead of taking just one point Q, you can take 2 points, Q1 and Q2. Then you do the same. So you blow up the indeterminacy point corresponding to the point Q1, and you blow up for the transformation eta index Q2. Okay, so you choose points in there, and you do the blow up. Now the good thing is that because eta is just the identity on the curve, when you do the blow up for the first transformation and then the blow up for the second transformation, and the first transformation does not move the blow up, the new curves that you needed for the second one. Okay. So this property implies, so this needs some work, but it's easy to show that doing that you get involutions in the group of automorphisms of the surface. So when you blow up everything, let's say the surface is Y. Okay? So you get K involutions in this group of automorphisms. And so, for instance, if you have at least 3 points and you compose the 3 first involutions, what you will get is a regular automorphism of a rational surface with a nice dynamics. Okay. Okay. So these are the main examples that I have in mind. So we have examples on tori, we have examples on K3 surfaces, and we have examples on rational surfaces. So all of them here, you see, depends on parameters. Here the parameters are given by the lattice. Here it's given by the choice of the polynomial equation. Here it's given by the choice of the cubic curve and of the points on the cubic.
So can you say what the automorphism of these guys generate the automorphism group or something? Or?
I think so, but I didn't verify, so I don't want to state it on this.
Okay.
What is known is that there are no non-trivial relations between these involutions if the K points are distinct. I don't know whether this involution generates the group of automorphisms. I think so.
But when you change your parameters, you simultaneously change the phase space and the dynamics.
Yes. When you change the yes. I mean, in all the, so it depends on what you mean by changing the phase space. So you can say that you change the complex surface. When you change the parameters, you change the complex surface. So in the sense that typically 2 surfaces in your family are not biholomorphic. But as 4-dimensional real manifold, they are diffeomorphic. Okay. So you can say that the manifold as a real manifold is fixed, and you change both the automorphism and the complex structure together. Okay. Okay, these are the main examples to keep in mind. So yes, so the strict transform of the cubic, yes, you take the pre-image of the cubic, but you remove the curves, the exceptional curves. Okay, so you take the strict. So I don't know how much of algebraic geometry you can take the strict transform of the cubic. It's a curve. It's an elliptic curve in the surface Y. And this curve is made of fixed points for all these automorphisms. From the algebraic geometric point of view, it's an anti-canonical curve, which is invariant.
When you say there are no relations, so do you mean they generate a free group?
Yes, there are no relations. So this, the group generated by these involutions is isomorphic to Z mod 2.
And kind of coming back here, so you said that this kind of free group is large, I mean, so it has like a...
So this group contains a subgroup of index 2, which is a... I mean, contains a finite index subgroup, which is a free group. A non-abelian free group.
Yeah.
Okay, so now I want to start the... So we have examples, and I want to start the description of the dynamics. So that's 3. So I want to discuss entropy and action on cohomology. Okay, so first, what is entropy? So it's not exactly the same as the entropy of this morning. So it's here. It's I want to look at topological entropy. So you have a transformation f of x. So it's a holomorphic diffeomorphism, but let's look at f as just a continuous transformation of a compact space, and you put a metric on x or on a metric, a compact metric space, and then you fix epsilon, positive number. So it's a precision at which you look at the dynamics. So now you say that x and y have the same orbit at, let's say, at scale epsilon during time of observation, which is equal to n, if the distance between x and y is less than epsilon. So you cannot distinguish x from y at scale epsilon. But also the distance between their iterates is less than epsilon for all k between 0 and capital N minus 1. Okay, so for you let the dynamical system evolve. You look at it at every step of the iteration, and you try to decide whether the 2 points are different at precision epsilon. So if you cannot distinguish the two orbits, you say that they have the same orbit at scale epsilon. Okay. And now you just count the number of orbits that you can distinguish. Okay, so let's say capital N, the number of orbits of F at precision epsilon is just the number of orbits that you can count. Oh yes, excuse me. Okay. And then the topological entropy at scale epsilon is just the exponential growth rate of this number of orbits. Let's move here. Okay, so you put 1 over n log number of orbits for F during time n. You take the lim sup of that, and then you get a number, and you let the precision epsilon be better and better, so epsilon going to 0. So when epsilon goes to 0, you can distinguish more and more orbits. And this is called the topological entropy of F. So Misha introduced the notion of entropy with respect to an invariant probability measure. And in fact, this number is the maximum of all entropies that you can compute with respect to all possible invariant probability measures for F. Okay, so that's the theorem. Okay, so this.
And there is no normalization.
Okay. No, there is no normalization in terms of epsilon. The point is that this number does not depend on the choice of the metric. I mean, if you change the metric in an equivalent metric, you do not change the value of the topological entropy. Okay, if you conjugate the map F by a homeomorphism G, you do not change the value of the topological entropy. Okay, so it's something which does not depend on the metric. I mean, once you fix the topology of X, and which depends only on the conjugacy class of F. Okay, and so it's a number which tells you somehow the complexity of the dynamics in terms of number of orbits. Okay, so for instance, if you take as Misha did this morning, so you take a polynomial transformation of degree d in one variable, and you look at P as a transformation of the Riemann sphere. So here X is the Riemann sphere. Then one can prove that the topological entropy is just a logarithm of t. Okay. If you take an isometry of a metric space, then the topological entropy is 0. Okay. Okay, so there is this formula here can be generalized, and I want to state the theorem which generalizes this formula. So let me explain the theorem. So, let's do that. So it's due to Gromov and to Yomdin. So you take M compact Keller manifold. So for instance, you can take a complex projective variety. And now you take F from M to M, a holomorphic transformation. So for instance, an automorphism of a complex projective variety. And you define rho of F. So it's a spectral radius of F star, of F acting on the cohomology of M. So, okay, so this is the sum of all cohomology groups, and F acts on this vector space, acting just on cohomology, and you take the spectral radius. So it's a limit when n goes to infinity of star n 1 over n. So it's the largest eigenvalue of F. Let's put C here. Once you take the modulus, the absolute value of the eigenvalue. Okay? So then the formula is that the topological entropy of F is equal to the logarithm of this number. Okay. So in fact, there are two parts in the statement. The first one is that the entropy is, the first one is that the logarithm of the spectral radius is a lower bound for the entropy. So the entropy is larger than that. So this is true for all smooth diffeomorphisms of compact, real compact manifolds. Smooth, I mean C infinity. So that's Yomdin lower bound. And the upper bound, so the entropy is at most equal to the logarithm of the spectral radius, comes from the fact that M is Keller and F is holomorphic. Okay, and that's Gromov theorem. The point is the following. So when you compute the entropy, you see what I'm doing. I'm looking at distances when I iterate F. One way to state it, you are trying to cover the graph of the iterates of F. So you take set of points like x, f of x, f2 of x, fk of x, let's say Fn of x. So you take the iterated graph of f in x to the n. And what you are trying to do when you look at these orbits that you can distinguish, you are trying to cover this graph by cubes in x to the n of size epsilon. Okay? So the number of cubes that you need is this number of orbits, roughly. Okay? So this number of cubes that you need is obviously it's related to the volume of the graph. Okay? But the point is that there are two main observations. The first one is that in Keller geometry, so here f is holomorphic, so this iterated graph is a holomorphic, it's an analytic subset of x to the n, and complex analytic subsets are minimal in the sense of Riemannian geometry. They minimize volume, okay, locally. If you perturb them, then the volume grows, okay? So that's the first observation. And the second observation is that when you compute volumes in Keller geometry, the volume of the graph is given by the integral of the Keller form to the dimension of x on the graph. And this computation, you can do it in cohomology. Okay? Because the Keller form is closed, and you can do it in topology, in cohomology. So these are the main reasons why this formula is, I mean, why you get this upper bound. Okay. Okay, so now what I want to do, I want to look at the action of f. So I come back to automorphisms of surfaces, and I want to look at the action of f on the cohomology and try to understand this spectral radius and try to understand what I get from the action on cohomology. So let's say first I'll describe the Hodge decomposition. Okay, so let me start. So x is, I come back to the case of surfaces. So x is a surface. So you have a cohomology group in dimension 0, 1, 2, 3, 4. And let me look at the second cohomology group. Okay. So then you can decompose it. That's Hodge decomposition. Okay, so here, let's look at the middle part, H11. So this corresponds to classes of closed forms of type 1, 1. So I mean, sum of aij of x, dxi, dxj, and so on. Okay. Here, this corresponds to closed form of type 2, 0. So I have just locally, I have just two coordinates. So locally, it's like phi of xy, dx, dy. And in fact, being closed here means that what you are looking at holomorphic 2 forms in X. Okay. So classes here are represented by holomorphic 2 forms. So the complex conjugation here, it's permutes H02 and H20. And here the complex conjugation acts on H11. So the set of fixed points is just H11 of X with real coefficients. Okay? And so this decomposition is invariant by the group of automorphisms because it's given by the holomorphic structure. Okay, so the action of F, here it's the action on the cohomology. If I look at the action on the second cohomology group, you have an action here, an action on H11, and another one here. The action on H20 is a little bit boring because if you take a 2 form, a holomorphic 2 form, okay, so a holomorphic 2 form, like this one, you can compute the integral over x of omega wedge omega bar. Okay, so this number is a positive number if the 2 form is not 0. And this formula gives a Hermitian product on this H20. And when you let the automorphism F act on this formula, then what comes out is the topological degree of X, and it's 1 because F is an automorphism. So here, the action here preserves a positive definite Hermitian product. So all eigenvalues here are equal to 1 in modulus. Okay? So they don't contribute to this spectral radius. Okay. So the same is true for H02. And I just have to look on H11. So why do I focus on H2? The reason is if you look at H1 of X, then you have a similar decomposition. H10 corresponds to holomorphic 1 forms. But if you take a holomorphic 1 form and you take the product with the complex conjugate of it, then you get a 1-1 form. So if you get an eigenvector here with eigenvalue lambda, you get an eigenvector in H11 with eigenvalue lambda lambda bar. Okay? So the spectral radius on H11 is at least the square of the spectral radius on H10. Okay. Okay, so now I focus on H11X. And I can use, real coefficients. Okay, so if I take two classes, U and V in H11, I can take their product. So let's say that's U dot V. I integrate the wedge product of U and V. Okay, so it's a number. And this gives a quadratic form on this vector space. Okay, so it's in the intersection form. And Hodge index theorem says that the signature of this quadratic form is 1 n minus 1, where n is the dimension of this space. So the intersection form is non-degenerate and of signature 1, let's say, H11 minus 1, where this is the dimension of the vector space. Okay, so geometrically this means that so that's a picture of H11. Here it's the isotropic cone. So it's a set of classes U such that U intersected with U is equal to 0. Inside the code here, the intersection form is positive. So if you take a vector here, the self-intersection of the vector is positive, and here it's negative. Okay, and this, you see, this intersection form is invariant under the action of the automorphism group. Okay, so I can use this form to describe the the possibility for the action of an automorphism so let F be an automorphism of X, and assume that, let's say, what I call lambda, which is just a spectral radius of F star on H11. Okay, so assume lambda is larger than 1. Okay, so I'm just assuming that the spectral radius of F on the cohomology is larger than 1. Yeah. Then, so first, the eigenspace, let's say, corresponding to lambda, so a set of vectors in H11 such that F star of u is lambda u. So this space, so it's the eigenspace for lambda has dimension 1 and is contained in the isotropic cone, so in the set of vectors with self-intersection 0. Yes, yes. Sorry, real coefficients.
Spectral radius is actually real.
Yes. What else? In fact, beta is an eigenvalue. So let's say beta in C, an eigenvalue of F. I mean, there is an issue with real and complex coefficients. I mean a spectral value of F star. Okay. So a root of the characteristic polynomial of F star. H11. Then beta is in lambda, 1 over lambda, or the unit circle. Okay, so either the modulus of beta is 1 or beta is equal to lambda or 1 over lambda. 3. The closure of the Keller cone of X intersects W lambda minus the origin. And 4. For all class U in H11 XR, such that self-intersection is positive, then the sequence 1 over lambda to the n F star n U converges toward the point V in, so V which depends on U in W. Yes, I will describe the Keller cone during the proof. Yeah. 3 minutes for the proof. Okay. Okay, so the first remark is the following. So I think you know Perron-Frobenius theorem. So if you take a matrix with positive coefficients, okay, then such a matrix, so you take a m by m matrix with positive coefficients, then you let the matrix act linearly on Rm, and it preserves the cone of vectors with positive coordinates. Okay. And the Perron-Frobenius theorem says that there is an eigenvector in this convex cone which corresponds to the spectral radius of the matrix. Okay, so and here you have exactly the same phenomenon. You have a cone, which I erased here. You have a cone which is invariant, so it's not, I mean, it's a round cone, but you have a similar theorem which says that if you take an element in the interior of the cone, and you take the forward orbit of this element and you normalize, then it converges to a dominant eigenvector, an eigenvector for the spectral radius. So it's Perron-Frobenius theorem for invariant cones, convex cones. So it tells you that the dimension of this is positive, and W lambda intersects. Yes, thank you. Intersects the, I mean, this convex cone. Okay. So at least what we know is that lambda, which was defined as a spectral radius, is in fact an eigenvalue of F star. And moreover, there are eigenvectors which are in the closure of this cone. Okay, so the dimension is at least 1 here. So now, why is it isotropic? It's just because since lambda is bigger than 1, when you compute F star of U, I mean of the self-intersection, it's preserved, but it's multiplied by lambda square. Okay, so U is isotropic. Now this cone, you see this means that W lambda is contained in the boundary of the cone. The boundary is, I mean, this is strictly convex, so it does not contain any flat of dimension 2. So the dimension has to be 1. It's a line. Okay, so this proves the first property. Okay. Now F star preserves the intersection form, so the determinant is plus or minus 1. So you know that there is at least one eigenvalue which is smaller than 1 in modulus. Okay? And you apply the same argument for the inverse of F, and you get another line here in the boundary of the cone. So here you have W lambda, and here you have another eigenvalue which is less than 1. Okay? And now you take the orthogonal complement of these two lines. Okay, so if we take a line in the isotropic cone, and you take the orthogonal complement of this line with respect to the intersection form, it is the plane which is tangent to the cone and contains the line. Okay? So this line is invariant by F, this one is invariant by F. So the two orthogonal complements are invariant, but they correspond to two hyperplanes which intersect here, and the intersection is entirely contained in the part of the space where the intersection form is negative definite. So here on this intersection of orthogonal complements, the transformation preserves a scalar product. So all eigenvalues have modulus 1. Okay, so you get at least, so what you get is here it's lambda, here it's modulus 1, here it's less than lambda, but since the determinant is 1, this is 1 over lambda. Okay, so that's checked. Okay, so what is the Keller cone? The Keller cone is the set of classes which are given by Keller forms. So if you have a Keller form, it's a closed form. You get a class in H11. And this cone is contained inside this convex region here, because the integral of omega, wedge omega, is just a volume of x with respect to the Keller metric. And now if you, so let me prove 4 and then 3. So 4, it's obvious because, you know, here it's acting with modulus 1 on this space. It multiplies by lambda on W lambda, and here it's a contraction. So when you do that, you just converges toward the W lambda. And then you apply 4 to a Keller class, and you get a sequence of Keller classes converging to W lambda. Okay. So it's time for a break, I think. I think that's tea time.
Questions?
Okay, so during the second talk, I will explain what I will explain. I will explain that in fact these classes in here are represented by classes of currents which are related to the dynamics, as this morning with this G plus G minus mu plus E minus. And how we can use that to describe the dynamics. Up to now, the dynamics did not appear. Yeah. Okay, thanks.